Good morning, everyone. Welcome to our virtual lecture on stoichiometry and single replacement. That is the title of our experiment this morning. This is second to last lab. Our last meeting will be on Wednesday. This coming Wednesday, it's gonna be a dry lab. More information will be sent out today. As far as this lab is concerned, I know you have covered the concept of chemical calculation, mole concept. In order to understand this, I would recommend that you go back to those relevant sections. So before I walk you through the procedure, what you will do in each step, I want to kind of like go real quick overview for stoichiometry. When we say stoichiometry, let's define or break down the titles. Stoichiometry, all right? This is quantitative relationship between, you define this as quantitative relationship between reagents, all right, and products in a chemical reaction. Quantitative relationship between products and reagent in a chemical reaction is basically what we call the stoichiometry, all right? There are prerequisite skills you need to have in order to master stoichiometry. Prerequisite skills are balancing the equation, all right? Balancing the equation needs to, that is what you need to remember in terms of the balancing the equation to master the stoichiometry. You need to, all right. You should be able to. Let me share my screen. Sorry about that. Should have shared that so that you see the definition. This is what I was actually defining the stoichiometry. Stoichiometry is quantitative relationship between, between the reagents and product. That's what I started with. And for this is what I was saying that you need to have beforehand. Balancing the equation is a concept you need to have. I know you know how to balance the equation, making sure that products and the number of mole atoms on either side of the reaction are balancing chemical equation is a prerequisite you need for you need in stoichiometry. The concept of expressing concentration of a solution using the molarity, simply number of what? Number of moles of volume in liters of solution. This is equation 1. All right, this is equation 2, equation 1 and 2, balancing the equation so that we know the mole ratio. Molarity, uppercase M, stand for the number of moles of, all right, number of moles of volume in liters of solution, not of solvent, of solution. You should be able to, these are the type of stoichiometry, type of stoichiometry, all right. There is mole to mole, all right. That means you are converting from mole to mole using the balanced equation, mole to mole stoichiometry. and you need to have mole to mass, that is changing from moles to mass using the molar mass, all right. The I'm not going to dive into other types of stoichiometry, but what is relevant as far as this lab is concerned are the two types of stoichiometry you see here: mole to mole using the balanced equation or the mole ratio, mole to mass using the molar mass of the reagent. This is something you covered before. Let's look at the molarity concept. Here, you can rearrange, remember number of moles, you can rearrange the equation to get the number of moles, which is given by molarity. All right, you can rearrange that to get the number of moles, molarity times volume in liters of solution. I don't know why my whiteboard is slow today. All right, this is the equation you need to know how do I find the number of moles if I know the molarity and I know the volume in liters, because you're gonna be using this, you're gonna be using the blue stab in your lab kit. That is one of the reagent and it is in a solution form. You should be able to find the number of moles using the equation I just gave you on the whiteboard, all right, by multiplying the molarity. We will see later on it's labeled 1M stands for molar. Molarity is 1. And of course, the volume you will measure will be in graduated cylinder. That means the volume will be in what? In milliliters, and you can change to liters. Recall 1 liter equals to 1,000 ml. That's what you will need to convert your volume. Always work with volume in liters. There is another standalone, all right? Let me just use this as equation 3. There is another standalone. There is another standalone equation for finding the number of moles, which we will also use, all right, in this experiment. And this is the number of moles, all right. Number of moles is given by mass in grams, all right, of molar mass or atomic mass, all right, molar mass of atomic mass. You can get the denominator right here from the what? This is from the periodic table, PT for periodic table, periodic chart. It's the same thing. It could be also atomic mass. This could be atomic mass of the chart, right? You can just have the atomic mass of the periodic table to get the number of moles. So this is equation 4. I'm giving you this equation so that when you complete the data sheet, you'll be able to figure out which equation am I using. If you are working with the solid reagent, you'll use equation 3. This should be 4. Yeah. You use equation 3 when you will be calculating the number of moles of the copper-2 solvent. And you will use also, one of the reagent is the aluminum foil. If you don't have aluminum foil, you can borrow yours from the kitchen, all right? You can borrow yours from the kitchen, aluminum foil. We will measure this and determine the mass, all right? How will we find out the number of moles? You may not see from where you are, but this is the aluminum I'm holding. We will use equation 4 to find the number of moles of known grams, all right? If I can weigh using the palms, you should have a palms in similar to what I have on my hand. I know you may not see, this is a palms with just stand on this. I know you have something similar to this, all right, which you can use to weigh your reagent 1. So these are the 2 reagents we're gonna be using. We're gonna be using this. Now, having said that, those are the equations I just kind of like gave you. When you look at the data sheet, you may wonder, how will I move forward with this? How do I determine the equation? In single replacement, if you look at the equation, single replacement reaction, previously we looked at single replacement reaction in the lab on investigating chemical reaction. And today, the two reagent will be working with this aluminum, all right? The aluminum foil you have, and make sure you write it solid, all right? It's slow, you may not see from where you are. It's reacting with copper 2 sulfate. You should be able to write the chemical formulas for your reagent. This is aqueous, all right? Aqueous, it is in liquid, all right? It is in liquid form, so aqueous, dissolved in water. This will replace, all right, it will replace, aluminum will replace copper. If you look at the where aluminum is on the activity series, all right, on the activity series, you will see that aluminum is more active. Aluminum is more active than copper. If you look at the screen, we have aluminum on this side at the top compared to copper below here. So it's going to replace. It will replace. Copper in this reaction here. In the reaction shown here, copper will, aluminum will replace. You should be able to write the chemical formulas. This will form aluminum ion in solution, and it is combining with copper with a sulfate. So the correct formula for that will be what? Al, 2 from sulfate, and in parentheses SO4 with a subscript 3 from aluminum. Doesn't cancel out. This will also form copper solid. This is aqueous. It's gonna be aqueous plus copper. This will be solid. We are going to, the objective is to synthesize copper. This is our final product. We want to determine the mass at the end. The mass of copper at the end, right here, is what we are trying to determine the yield, all right, to yield. At this point, the equation is not balanced. Remember the basis for stoichiometry, the equation should be balanced. Using trial and error, we need to balance the equation. For example, I can say that I do have 3 sulfate. You see here, we have 3 sulfate here. Don't break it into sulfur and oxygen. It's gonna be too much. Read this as 3 sulfate, and we need a 3 in front of copper 2 sulfate. Copper 2 sulfate. We need a 3. Why? Because of 3 what? Because of 3 sulfate on the product side. So 3 times 3 sulfate, it should be sulfate, yes. 3 times 1 is 3, 3 times 1, so the sulfate is balanced out. I'll say sulfate is balanced out. Let's see, aluminum here, I do have 2. We need a 2 in front of aluminum. That's how you balance the equation. And here, I do have, all right, I do have 1 copper. I need to balance the equation. So what do I need? I need to have 3 here. I need to have a 3 to balance out the copper on either side. So mole ratio is, I can say mole ratio here is 2 for aluminum to 3 for copper 2 sulfate to 1. You don't see anything here, but 1, all right, but 1 for aluminum sulfate and 3 for copper. That is the mole ratio we call, or that's how you write the mole ratio. We need this in order to determine the limiting and excess reagent. All right, you know the limiting and excess reagent. When you mix 2 reagent does not mean that, you know, all of them will run out. One of them might run out fast. We call that limiting reactant. The one which will be left over is the excess reagent. The coefficient in the balanced equation does not tell us that 2 grams react with 3 ml. No, this is the geometric mole ratio. So at this point, the objective for this lab is to find how many grams of this is question mark, and to say not 2, but I want to say here how many grams of copper will be produced. We need to know this so that we compare the theoretical and the experimental. We have what we call experimental. That is what you will get from performing the experiment, yield, and theoretical yield. All right, we need these 2 types of yield. The first one, experimental, is what you will get from the experiment. The later one here, theoretical yield, you obtain this from the limiting reagent, all right? By knowing how many moles of each reactant, all right? By knowing how many moles of each reactant you will use, you will be able to determine which one is the limiting reagent, and the amount in grams of the copper, we care less about the sulfate here. This is just what we will use, this is what we will weigh at the end to find the experimental. There is the experimental yield you will get from the experiment, and there is the theoretical yield you will get from the limiting reagent. With these two, later on or towards the end, you will find the percent yield, all right? Percent yield is obtained from experimental, all right? Experimental yield of theoretical yield times 100%. This is what you will use to find the percent yield of your reaction. This is what chemists use, and good percent yields, good experimental setup, and you know, devoid or minimizing experimental error anywhere 8 and above is, you know, is considerably acceptable. Not something like 15%, you know, that does not gonna work. I mean, that is not viable. With that, you'll be able to complete the data sheet. You'll be able to complete the data sheet. Before I walk you through the data sheet, let's just pick up some numbers, all right, so that you can relate, or you can plug in your values you will use today, all right. When you collect the data, you will plug in your values respectively so that you end up with the right values. I'm going to pick up some random numbers. Let's say I'm using 60 ml of 1 molar. This is 1 molar. M stands for molarity, 61 molar. And say I'm using 1.5 grams of aluminum. That's just, you know, the mass I've done. I've weighed this. That is 1.5 grams, and I'm using 60 ml of the blue stuff. The blue stuff in the Ziploc, little bit Ziploc, and this is. I'm just going to mix them in. There is a beaker. I'm just gonna mix that. Make sure that it is dissolved completely. Copper. This will be produced, and I want to know how many grams will be produced. I'm putting a question mark. How many grams? Let me even put grams right there. That how many grams of copper am I expecting? Out of what? Out of 1.5 grams of aluminum and 60 ml of copper 2 sulfate solution. In determining the theoretical yield, all right, we need to find the limiting reagent. And the limiting reagent, the amount obtained from the limiting reagent is your theoretical yield. Let me rephrase it again. The limiting reactant gives you the theoretical yield. The reactant which gives you less amount of the desired product will be your limiting reagent. Let me back up to my values here, all right? My values of, how much I'm going to take. If all these grams of aluminum are consumed, how many grams of copper will be produced? If all the 60 or all the amount of moles in 60 ml, not the consuming 60 ml, how many moles do I have in 60 ml? Once I figured out the number of moles in 60 ml of 1 mole of copper 2 sulfate, how many grams of copper will be produced? So if I know the grams from each reagent, I'll compare the two values. From aluminum, how much do I have? From copper 2 sulfate, how much do I have? The one which gives me less amount will be my what? Will be my limiting reactant, and that will be the theoretical yield. So I'll say, all right, if AL is limiting reagent, I'm just writing L, for limiting reagent, LR for limiting reagent. This is how you set up the equation. Start off with what you are given. It is 1.5 grams of copper, please. No, aluminum, not copper. We're using aluminum. Using the molar mass, we have to find the number of moles. This is the grams of aluminum here. I want to find the number of moles. So here will be moles of AL, all right, AL there. And the molar mass is 2698. This is 26.98. Aluminum will cancel, aluminum will cancel. After that point, I have what? I have changed the 1.5 grams of aluminum to moles of aluminum. And then using the mole ratio between, this is 1 mole of aluminum, copper and aluminum was 1 for every 2 moles of aluminum. AL, 3 moles of copper are produced. I'm using the mole ratio from the balanced equation, mole ratio. And then the last one here, to find the mass of copper, you use the atomic mass. Copper is 63.5. This is 1 mole of copper, 63.4, 54. This is 546. 546. This is grams of copper. So that moles of copper will call moles of copper, aluminum and aluminum. Right here is atomic mass of AL. This right here is the mole ratio. And here is the atomic mass of what? Of copper. Atomic mass of copper. So that you know where the numbers are. This is stoichiometry, what I'm doing right here, using the atomic masses and using the mole ratio. The numbers here are from the balanced equation. So with my calculator, let me see how many grams I have. So if I multiply everything at the top, this will be 1.5, all right, times 3 times 63.546. I'm multiplying everything at the top fast and then divided by 26.98 divided by 2. All right. So this gives me 5.2. All right. 2. I think 33. Let me 30 because 99 is 5.2994. Let me just 3 significant figures. This is grams of copper. What this tells me is if all 1.5 grams of aluminum are consumed, if it is the limiting reagent, that is the amount of copper you expect from the reaction. And then you say you do the same thing. Suspect that if this one, if copper 2 sulfate is a limiting reagent, all right, what is the gram of copper? What is the grams of copper which will be produced? That's the question. Since this is liquid form, we're not going to use the molar mass. In the stoichiometry, you have to find first of all number of moles. All right, number of moles of copper 2 sulfate in 60. Remember, I was using 60 ml. Yours will be different. From the molarity, number of moles is given by the molarity times volume in liters. Molarity is 1. All right. Moles per liter, per 1 liter times 0.060 liters. What I've changed there is change the 60 ml to liter so that this will cancel out and that will cancel out. So I have what? This will be 0.060 moles of copper 2 sulfate. You have to find the number of moles first. You have to find the number of moles of copper 2 sulfate. And then from there, you can now find the grams of, therefore, grams of copper from 60. 60 ml copper 2 sulfate. The number of moles here, 0.06, all right? This is 0.060 moles of copper 2 sulfate times the mole ratio between copper 2 sulfate, all right? I think it was 3 to 3, all right? From the mole ratio, for every 3 moles of copper 2 sulfate produced, consume 3 moles of what? 3 moles of copper are produced times 1 mole of copper. The molar mass 63.543. This is a molar mass of copper. So that doesn't cancel this and that will cancel. And I think one and that one just cancel. So here, if you multiply 0.060, all right, times 63.543, that will give you 3.81, all right, 3. This is grams of what? This is grams of copper that will be produced when 60, or when this number of moles in 60 ml of copper 2 sulfate are produced. I'll compare now 318 and 5.2, 5.2 or 5.30. This is weight. So my limiting reagent is copper 2 sulfate solution, and the theoretical yield, this is called theoretical yield, all right? If let's say you perform the experiment, or I perform the experiment based on my numbers I just pick randomly, and this is the expected. I expect that I just weigh, you know, the aluminum and maybe something I don't transfer quantitatively, something else happened, maybe experimental error. If my experimental yield, all right, is 3.68 grams of copper, therefore percent yield will be given by, all right, experimental over theoretical times 100%. So this will be 3.68 grams of copper over my theoretical 3.81, all right, 3.81 grams of copper times 100%. This will give me, all right, 3.68 divided by 3.81, and I have times 100 is 96.6%, which is not bad, you know. This is good. This is what you will do, all right? This is what you will do in the calculation part of the experiment today. This is what you will do in the experiment part of our lab today. Now, there are, all right, there are items you have to learn from your, all right, you have to learn from your kitchen, all right. There are some which are not available. You will need to use the table salt, which is a catalyst. Let's talk about the catalyst, all right. I've walked you through on how to find the theoretical yield, how to calculate the percent yield. I'll just fast forward to the procedure. You can read this. I just, you know, this step right here is pretty straightforward. You can understand. Forget about the balancing the charges. So long as you can balance the equation, which I've walked you through, using the molarity equation to find the number of moles. That's what you will use today, and determine the limiting reagent. I've given you that. What I wanted to fast forward is the procedure and maybe demonstrate some of the, you know, techniques. These are the items you will need. I received an email, somebody was missing 1 or 2 items. Please, if you are missing anything, please let me know. If you are missing something, probably because they want you to pour from kitchen, for example, sodium chloride. It's not readily available. They mentioned that. You see, there are no suppliers. A ruler, you're gonna need a ruler to measure the dimension of aluminum foil. Paper towel, sodium chloride, about 1 gram. You don't need a lot, all right? So with that, these are the items: the funnel, the filter paper, all right, the weighing board, and the picker. This is the solution, 1 molar. You're gonna need about 100 ml of that. Let's see the procedure here. How are you going to carry the experiment? You're gonna need an oven to dry that, set to about maybe 250. This is for drying your copper. See you at the end. Now, you will measure your fast reagent here twice, as it might be less than, and that's why you have to confirm. Even though it is indicated that it's 100 ml, some might have less than, maybe 98. So you have to measure twice using 50 ml graduated cylinder, approximately 100 ml. So because of the capacity, you know how to read the meniscus. You will pour it on a flat surface. You have the meniscus at 50 ml twice. If the second one, if the second portion does not add up to 50 ml, just record the total volume of copper 2 sulfate. That is what you will put in your data sheet. All right, in the data sheet, you will. All right, you will have the volume of copper 2 sulfate. Let's see how you will put there. Copper 2 sulfate. This is where you need to put in volume. All right, and you may not have enough. You may not have enough space here to show your work. But feel free to, write the title, volume of, 1 molar copper 2 sulfate, mass of aluminum foil. I know you can get that. Number of moles using the equation. I know you can get that easily using the equation I gave you. You will have to, all right, cut the aluminum foil. Once you measure that, you have your solution here. Please do not use the calibration on the, on the beaker and say, it's not gonna work. Use that and record the total volume. Make sure you have table salt in there. It acts as a catalyst. You know what a catalyst is? It is reagent added in there so that it speed up the reaction. So measure out, approximately. It doesn't have to be exact, so long as it is around this 1.5 or 1.4 to 1.6. If you have 1.8, they recommend that you chop a little bit. Don't have to have exact 1.6 or 1.5, so long as it's in this domain. Once you have that, assuming that assuming that you have measured this, you'll have to cut into small pieces without losing any piece. I'm just gonna cut that. You may not see that into small pieces in such a way that you increase the surface area and add in there. It will, reaction will be exothermic. It will be warm, not hot, all right? Not hot enough to, burn the plastic. The rest of the direction is pretty straightforward, but I want to demonstrate or show you how to do the filtration. There will be copper, all right? There will be copper at the bottom of the beaker. That is your product. That is what you want to isolate, dry, and weigh. And first, there will be the liquid part of it, called the supernet. You want to decant. Decanting is pouring. Having this copper in there, you pour it slowly without transferring everything across. You want to dump the liquid part and have the copper in there. That's what you will need to filter using the gravity filtration. I recommend that you use the graduated cylinder for gravity filtration. And I think I placed somewhere my funnel. I had a funnel somewhere here, which you need to set on, right here. This is a funnel. You know what it look like? I know you can see that. You will set it up in such a way that it is sitting on the funnel. Graduated cylinder. All I see all the time, students struggling on how to work with the filter paper. As a filter paper, you fold it into half like that. You see? Fold it again, and the direction goes just like for, you know, tearing one part. If I tear one part, whatever I tear will be, I will not use for filtration. You see, somebody will just put it in the funnel width. You may not see there. I don't want you to put it in the funnel side that your sample will go through this space. Look at the cursor. You want to have a complete cone. A complete cone, when you look at it through, you cannot see anything, all right? Like it's a perfect cone like that. I don't want you to have something like, you know, you may not see it from here, but one side with a perfect cone, when you look at it, it's a cone, and then you moisten it. It will not really sit perfectly, but you want to press it down in the funnel. It may not hold. You have to sprinkle water until it is sticking on the wall of what? The wall of the funnel. That's when you place it now on the graduated cylinder. With your solid copper here, you want to filter it through gravity filtration until everything is quantitatively. You can use the pipette. You squeeze water here to wash it. You sprinkle with, you know, if I have the eye water or just the water, I'm gonna use the pipette. This is called the pipette, the one you may have seen this. With water, I'm just gonna rinse it onto the funnel, So if this is my funnel, I'm just gonna rinse until I have everything on the funnel here. The rest of the direction will be straightforward on how to wash. You will wash these and carefully remove the funnel with the copper. There will be copper in here, similar to what you see here. You will dry in the oven. There are two ways. Either you let it for a day or you put it in an oven to dry. You'll have something similar to this. You'll use the paper towel, dry until this one is pure, you know, copper. You can tell when it is dry, that is kind of like powder. That is when you will now tear the weighing board. All right, you should have a weighing board. I'm looking for my weighing board with the wing. You're gonna tear that. You know how to tear, to zero it. So you're gonna place your weighing board on the palms and tear it. That is to zero. So if I have my weighing board here, I'll take, press to 0, and transfer your copper onto the tear and get the mass of, all right, get the mass of the copper, and that will be the actual right here. Actual yield is from the experiment. This is what you will weigh out. Percent yield, you will use the equation I showed you. Theoretical yield is obtained from the limiting reagent. You will see how I worked the example in the, you know, you'll have to replay. I'm just gonna post this video again. See how I use 1.5 grams of aluminum and 60 ml of copper 2 sulfate to determine the theoretical yield. The one which will give you less amount of the desired product, which is copper in this case, will be your the limiting reagent, and that will be the theoretical yield. With that, you know, I want to stop sharing my screen and take any question you may have before I stop sharing the screen. Yes, Diane, it is just a lab sheet. Somebody was asking a question. Yes, it is posted on the module, unless maybe something is wrong. Somebody had asked the question, you cannot find, let me see what's going on. To answer that question, it is on the module. If I go to module, make sure you go to module on the course. So if I do that, modules right here, unless maybe it is not published, I'll publish it right now. It is under right here. It is under, oh yes, right here. It was not published right here. You should see it now. You should see it now. This is under the module 11. Sorry about that. I hope that answers your question. So you'll see the, you should be able to see now the handout, all right? You should be able to see the handout right now. And the data sheet is on the assignment tab. You'll see that. So you should be able to see the handout. It was not published. It is published now, and it is pretty straightforward. Any other question? There is a handout I just published on Canva, so you should be able to use that as a procedure. Not the handout, no, it's not going to work with just the data sheet. You need the direction. So the document I was sharing with you, you should be able to access it right now. Any other question? All right, if there's no other question, I'll stop sharing my screen, and I'll see you on Wednesday, same time. If you have any questions, just send me an email and I will respond to you. The class is dismissed. Thank you for joining in this morning. I'll see you again on